Welcome to this lecture on machines, electrical machines, and in our last class we came up to this, that is you recall that at t equal to 0 plus we first observed what is going to happen, and we told you that frequency of the rotor current are one and the same. Rotor is yet to rotate, but it is carrying current. At t equal to 0 plus, speed still remains 0 because of its inertia, and rotor frequency at 0 plus is p by 2 into ns minus nr, which is p ns by 2, and then it is supply frequency f. At least one thing we have assured, we are sure about, that the stator field and rotor field with respect to a stationary observer, he will conclude that both of them are rotating with same speed, synchronous speed so called, at t equal to 0 plus, and therefore, it is expected there will be a constant angle between these two, and perhaps a constant torque will persist, and rotor will accelerate, and rotor will accelerate in the same direction as that of the stator field, because it is only in this direction the cause for which the rotor currents or rotor voltages are due will reduce. That is what Lenge's law tells us. So, rotor cannot but rotate in the same direction as that of the stator field. Then I am telling that okay, that t equal to 0 plus things is now over, time has elapsed quite a bit, so that rotor has started rotating in the same direction at any speed nr could be 2 rpm, 5 rpm, whatever it is. Suppose at some time the rotor speed is nr, stator field speed will of course not change, because it is connected to a supply whose frequency is f. So, stator field speed with respect to stator structure remains same, and rotor is now moving, and in my we know that the RMS voltage induced depends on ns minus nr, which decreases now from the instant at t equal to 0 plus. At t equal to 0 plus nr was 0, but it will decrease because ns minus nr is there, and so long ns minus nr is not equal to 0, there will be rotor voltage and there will be rotor current, and if there is rotor current, there is bound to be rotating field created by the rotor. Now, the question is, what is the frequency of the rotor current? Rotor is wound for same number of poles, and frequency of the rotor current will therefore be p by 2 into relative speed between these two. So, this will be the rotor frequency. So, if this is the case, frequency of the rotor current is this one, then speed of the rotor field, rotor resultant field, always it means that rotor resultant field, rotor field I will simply write, you understand now what is what. Speed of the rotor field will be equal to how much? It will be 2 Fr by P, so much mechanical speed. If rotor current is F, 2F by P, that is the speed of the rotor field is 2 Fr by P, because frequency of the balanced 3-phase current is Fr. For stator, frequency of the current is f. So, stator field speed was 2f by p. So, now it must be 2 Fr by p, it is no longer f, because machine has picked up some speed. Now, the question is, as I am telling, the moment I write this, I must attach a rider to this. With respect to whom? With respect to whom? With respect to the structure which houses the three-phase winding. Which houses the three-phase winding is the rotor body. So, with respect to rotor itself, this speed is 2 Fr by P with respect to rotor itself. So, that will be the speed of the rotating field. Okay. Now that is there. So, but it is 2 by P and Fr is once again P by 2 into Ns minus Nr, is not, and this will be equal to Ns minus Nr. Perhaps I could write straight away, but anyway it is good to do like this. So, this is Ns minus Nr, and do not forget to write that this is, and this is mechanical speed, either you remain in electrical or mechanical. Do not get mixed up one's electrical speed with another mechanical, either remain in electrical or mechanical. So, I am always remaining in mechanical speed. So, this is Ns minus Nr mechanical speed, and with respect to rotor. So, here is a rotor where there is a rotating field Br, and it is moving with a speed Ns minus Nr with respect to rotor itself, and a stationary observer also sees a rotor speed Nr with respect to the stationary observer. So, rotor is also moving in the with a speed Nr with respect to a stationary observer, and with respect to the rotor the field is moving with a speed Ns minus Nr. Therefore, the conclusion is, therefore, speed of the rotor field with respect to a stationary observer or in this case stationary observer and the stator structure, stator are one and the same thing, both of them are not moving, will then be equal to Ns minus Nr plus Nr, and that will be Ns. Therefore, to a stationary observer, he will always conclude whether the rotor is stationary or it is moving with any speed Nr. The speed of the stator and rotor field are Ns. With same speed, both of them will be moving like this. Therefore, the angle between them will remain time invariant, and therefore, we expect some torques will be developed. I am repeating once again these steps rather fast. See, speed of the rotor field is 2 by P into frequency of the rotor currents, and frequency of the rotor current is Fr, we have calculated earlier. So, 2 Fr by P will be the mechanical speed of the rotating field, and with respect to whom? With respect to the coils, rotor coils or rotor structure. So, 2 Fr by P with respect to rotor itself, and then you put the value of Fr, which I have already calculated, put it here, it comes out to be Ns minus Nr straight, mechanical relative speed. So, speed of the rotor field with respect to a stationary observer will then be that rotor is also moving. So, stationary observer will say Ns minus Nr plus Nr and is equal to Ns. and a stator field in any case it is moving with ns. That we have already concluded and decided, because the frequency of the stator current is always f, it cannot be other than f. Therefore, it is expected machine will develop a torque as you have been successfully created two fields and a observer, fixed observer, no matter wherever it is seated, the observer may be moving with some speed 1000 rpm, but he also should conclude that these two fields are moving at same speed. So, we have taken conveniently a stationary observer and the conclusion is okay, it will move with speed ns. Therefore, rotor will pick up perhaps speed. Therefore, this, if rotor is allowed to move, no lock, no rotor locking, rotor is allowed to move and the rotor circuit is closed, then only of course rotor current can exist and then only question of movement comes in, and this is how speed grows. So, this part, in this part I have shown that okay, rotor will create a field and rotor field speed is same as the stator field speed with respect to a certain observer, and they are same, and it is expected conclusion is to develop some torque. Acha, now the big question remains, okay, now interesting thing happens. See, I will just touch upon first, then we will come back to this point. So, what is the thing I have told? There is a stator coil. We ask ourselves, okay, this is what is this? This is R1, this is Y1, this is B1, okay, and there is rotor terminals. Which is RR, which is YR, this is 120 degree, please bear with me. So, and this is RR, YR and BR, and these things I have kept short circuited, rotor current is flowing. Now, and it is moving in this direction. Now, there is some BS moving when there was no rotor current, it was there. Now, there is rotor current, BR is also moving with same speed ns, and this ns with respect to a stationary observer, they conclude they are moving in the same direction when this fellow is energized, that is there. But now I am slightly not disturbed, but I now feel that okay, now in the air gap of the machine there are two rotating fields and both of them with respect to a stationary observer is moving with a speed ns. Therefore, induced voltage in any coil either on the stator or on the rotor, both Bs and Br is going to induce voltage. Br, why it is going to induce voltage in this coil? Because of the fact there is a relative speed ns minus nr between the coil and Br. Is Br is going to induce voltage in the stator coils? Yes, because stator coil is stationary and Br is moving with speed ns with respect to the stationary coil. Apart from Bs is inducing voltage here. So, these are the issues now. We must be knowing very clearly what is then going to happen. Acha, before that, so this I just raised this question so that you also feel like okay, something is to be done about this. So, what is then going to happen? For example, what I am trying to tell that in this expression flux per pole phi, what should be used? because in the stator coil E1 root 2 pi Pns by 2, both of them are moving no doubt with synchronous speed. This term remains same, but what is flux per pole? Which flux per pole should I use? Understood. This is the issues. This can be very nicely explained, and this will come slightly later. But I just leave this question to you to think over it over and over again. That is okay. Then what is what? Achha, before that, and also I am not sure. I told you BS, BR are produced and there must be some difference of angle. Both of them are rotating with same omega s, no doubt, ns. But how that angle is decided, things like that now becomes important. Although we have concluded machine is expected to run, what is the torque, how to relate the torque in terms of BS and BR. Achha, at this point at least you must agree with me that okay, one thing can be done. This BS is there, BR is there. I will take the resultant of these two fields. These two space vectors can be added in space and resultant field I will get, and with respect to that resultant field I should calculate this phi flux per pole. What the point? Because if you take the resultant field, then a lot of things will now get simplified, because of the fact you can assume BS is present, BR is present, or you can assume okay, BS plus BR resultant is present, and let us see, and because of that resultant field, because both of them are going to induce voltage in these coils, I will take that net field. I am giving you some hints so that you can further think over it. Achha, now whatever time is left, I will do another important thing, because the issue of the angle between BS, BR, things like that is to be resolved. So, to do this, what I will take? I will take a very simple example. Achha, this thing, whatever I will be doing now, I have taken from, although I have not told you any name of the books, I will tell you the name of the book in the next class, okay. But let us try to understand, very simple. Achha, suppose you have a stator field, BS, and you can imagine this stator field, it has nothing to do with induction motor, but this problem if you understand, you can extend this to induction motor, synchronous motor, what not. This is suppose your stator slots, stator coils, etc. And suppose for simplicity, let us assume there is a pair of slots, you are passing some DC current and there is a field which is created BS, let me call it BS. And this BS of course can be created by a distributed winding carrying AC currents, and this BS will move. But the problem statement you try to understand, suppose there is a BS which is stationary. Stationary is a special case of moving thing. Now, you must understand with ns equal to 0. There is a field which does not move. Okay, that is possible if you energize the stator coils with DC current, is not f equal to 0, ns will be 0. Anyway, DC current, suppose let us take a simple, of course, this can be a distributed coil, dot here, but I am using a single coil BS, and fundamental component I am sketching. Okay, this is BS. Achha, now suppose there is a rotor here. This exercise everybody must do to understand the torque production and how the angle between BS and BR etc. comes in. Suppose you have the rotor iron, and here also you have a pair of slots. This I will do slowly so that you understand. Two pole structure, and this is the rotor current cross dot, and therefore the rotor field will be perpendicular to this line. It was stator field was perpendicular to this line, is not axis of the coil. So, rotor field will be also perpendicular to this line. This is rotor iron, and let this be BR. Acha, I have put an arrow. What does that mean? It means the peak of the fundamental component of this BS, because I can distribute this winding and make it more sinusoidal, or only consider it will be rectangular, but fundamental component I am talking about. So, its peak is here, and what is this arrow means? It is the lines of force direction, no issues. So, this is also lines of force direction, and peak value of this current here is PR. Okay, that is fine. Now, as I told you, you study this topic not considering do not keep induction motor in your mind. Okay, this is a BS produced, a BR produced. I want to find out what will be the expression of the torque in terms of the angle between these two fields, say gamma. I want to find out. What should I do? Acha, you see, this is the cross current, this is the dot current. Let us assume that this angle is theta, and this rotor I have locked it. So, in this position, what torque it experiences, that I want to find out. Imagine rotor is not allowed to rotate. Stator you have energized with this current, it produces BS. Rotor you energize with this cross, this dot, it produces BR. It is expected that you see stator poles, this is south pole, SS I am not writing, and rotor, this is north pole. So, there will be an attraction between NR and SS here, and it is expected torque will be in this direction. I can physically tell that, but nonetheless I will apply left hand rule. For example, the magnitude of this current is IR, rotor current, and you know this is the direction. What will be the value of BS here? If BS is the peak value, so BS cos theta is not along this line like this. So, this B strength is BS cos theta. So, BS cos theta and IR is this current, and you can easily see the conductor will experience a force like this. And what will be the magnitude of this force? It will be BS cos theta, B I L, IL is the rotor current IR into L. L is the effective length of the conductor perpendicular to this length, we know. So, it will be just like this, and similarly this is just same placed, it will also experience a force in this direction. You can apply this current is cross, apply left hand rule, and magnitude of the force will be same. So, here are two forces, and the distance between them is the diameter of the rotor. Therefore, the torque, this coil torque or couple acting on rotor will be this magnitude of the force L IR BS cos theta into this d equal to dia of the rotor. This will be the torque acting and which appears to be in the anticlockwise direction like this. So, this is the force. Now, you see this IR, this can be written as some constant k into BR into BS into cos theta, because I know the fundamental component of BR, peak value of its, is directly related with IR, is not. Therefore, with some constant k, this dl also is getting absorbed in this constant, apart from whatever other H2B, mu 0, this, that. So ultimately the torque, electromagnetic torque, is this one cos theta, BR BS cos theta. What is BR? BR is the peak value of this sinusoidally distributed rotor flux density. What is BS? Peak value of this one. Now, and this angle is gamma, I have just defined. And what is theta? Theta is this. If theta is this angle, you note that theta is the angle between this line and this line. So, theta will be also the angle between their perpendiculars. So, this is perpendicular to this line and this is perpendicular to this line. Therefore, this angle too will be theta, is it? Therefore, this is the thing. My goal is to find out this expression of the torque in terms of gamma, say. So, gamma is nothing but, as you can see, 90 plus theta. Is it? Therefore, this expression of the torque is BR, BS, and cos of theta is nothing but gamma minus 90 degree, which is nothing but k BR BS sin gamma, because cosine 90 minus theta is same as cosine gamma minus 90. That is why cosine, okay, fine, very good function. So, this is the expression of the torque. And see, now I will just draw it here. It is BS, a vector, and it is BR at any arbitrary position BR. This angle is gamma. Is not? So, can it not be written as k into cross product of these two vectors? A cross B is magnitude of A, magnitude of B, and the angle between BR and BS. And this also gives you, see, BR, BS, if you multiply, thumb give you the direction of the torque. Direction of the torque means anti-clockwise. So, this is the important result, that electromagnetic torque developed by a machine, essentially if you know the position of BS, field produced by stator coil, and position of the rotor field at any instant of time, this is the torque experienced. What I told you in the derivation, rotor is not allowed to move. I have held it to understand really how much torque is developed in this position. Okay, if you release your hand, what you will observe? The rotor will move, and in this particular example, if these are DC currents, BR and BS will finally get aligned and there will be no torque. That game will be over. But in which way it is connected with induction motor? Okay, we are now matured enough that this Bs is created by some 3 phase current or whatever it is, and it is moving its position, that is also fine. Br is also produced by a balanced 3 phase coil, that is also moving, angle between them is remaining constant, is not, in case of rotating field we have seen. Therefore, I can apply the same formula to get the electromagnetic torque there. It will give me a clearer idea about how torque is produced, particularly as a motor operation or as a generator operation. So, we will continue with this today's lectures, that is the last 3 lectures. Please go through it very carefully, so that we can proceed further. After we have done this, it will be all nice. Thank you.